Okay, we're going to be working through part B of exercise 3 on page 97 of the workbook here. Okay, excuse me. Still getting used to this iPad. Okay. So, same question that we've answered a couple of times. They're giving us a linear operator and they'd like the eigenvalues and a basis for each eigenspace. What's a little unusual about this one is, there I go again, sorry. It's not so obvious to figure out what the matrix of our linear operator is in this case, okay, because our vector space actually contains polynomials here. We're not going from Rn to Rn, so what do we do in a situation like this? Okay, well, fortunately, we know how to find the matrix of a linear transformation, and so that's the way that we're going to start here. Now, the only catch to that is we need to choose a basis for our vector space, and probably the easiest choice of basis, you can guess it here, would be just to use the standard basis for P1 of R. Okay, that's the way that I'm going to start on this problem. Okay, so we'll let beta be 1x. There's the standard basis for P1 of R, and we're going to find a matrix for this linear operator that we've got. Okay, and the process for that, again, is just to take our basis vectors one at a time and just substitute those in and see what we get as an output. Our formula for t is sitting over here. So we plug in 1, we're going to get 6 times 1 plus x plus 5 times the derivative of 1, but the derivative of 1 is just 0. Okay, so out comes 6 for that first calculation. All right, and then t of x, same idea. This time we're going back to the formula up here again, and this time we're plugging in x. So x plus 5 times the derivative of p, but the derivative of x is 1. Okay, so if we do the calculation this time, we're going to get 6x plus x plus 5. Can you do that arithmetic in your head? That's going to come down to just 5 plus 7x. Okay, and remember, we're trying to build a matrix, so the 6 that we got up here on the first line, convenient to rewrite that as 0x, and remember that a matrix comes from looking at the coefficients. Okay, so if we take those coefficients and just build our matrix, we are going to get a matrix that looks like that. Okay, and so that gives us a starting point. We can find the eigenvalues of that matrix. This is just a 2 by 2, so this calculation is going to be maybe a little easier than the one in the last video. Okay, so we'll take that matrix, take A minus lambda I, meaning we're just going to subtract lambda from all the main diagonal entries. This is just a 2 by 2 determinant in this case, so we're just going to get 6 minus lambda times 7 minus lambda, and minus 0, because 5 times 0 is 0. Okay, so really, we don't even need to write that minus 0. And we can see what our eigenvalues are. They're just going to be 6 and 7 from those two terms. All right, so let's look at those one at a time. Okay, so for lambda 1 equals 6, we are going to go to our matrix up here and plug in 6 for both of those eigenvalues. That's going to give us 0, 5, 0, 1, it looks like. Okay, and I want to make a comment just about general notation here. Right, so you can see the system that we wrote down. And when we do the step of finding eigenvectors, we always have these two zeros over here on the right-hand side. Always, always, always. And so it gets a little cumbersome to have to keep writing that over and over again. And so often what we do is we abbreviate this. Just get rid of that last column. That's kind of understood that that's going to be there if we're finding eigenvectors. All right, so from here on out, I will probably not write that third column. You just kind of have to remember that we're really setting this equal to 0. Okay, and if we do row operations on this, we're going to come down to a matrix that looks like this. Okay, and you can see there's one pivot position there. Okay, and I'm trusting that you can solve this system again. We've got x1 being a free variable in this case. X2 is going to wind up being 0, and that's going to generate an eigenvector that looks like 1, 0. Okay, if we let our free variable be 1. Okay, again, I'm skipping a few steps there. All right, and then we can move on to our other eigenvalue. Okay, same process again. This time we're going back to our original matrix and plugging in 7 for all of our lambdas, and we're going to get -1, 5, 0, 0 in this case. All right, and that matrix is kind of already in echelon form. There's our pivot position, so this time x2 is a free variable, okay, which we can give the value of 1 to, and that's going to generate an eigenvector that looks like 1 for x2, and you can solve for x1 and get a 5 out of that. Okay, again, we just kind of chose the value of 1 for the free variable because it's continuous. Okay, well, now there's one more hurdle to get over in this problem. Take a look at our eigenvectors. Those are vectors in R2, but if you look back at our vector space consisted of polynomials, so our eigenvectors should really be polynomials. Okay, so here we have to remember that we found the matrix for our transformation, and so the way that we really need to interpret these eigenvectors is as coordinate vectors relative to our basis. Okay, and since our basis was simple, it's not too difficult to see the correspondence here. 1, 0, for example, that's just going to correspond to the polynomial 1 plus 0x. And 5, 1, that's going to correspond to the polynomial 5 plus 1x. So it's those two red things that we're circling. Those are our real eigenvectors in this problem. All right, and so we can go and state our final answer as follows here. Okay, scroll up a little bit. We'll make our table. Okay, in this case, we've got two eigenvalues. One of them was 6 and one of them was 7. And for 6, we came up with a basis for the eigenspace that looked like 1 plus 0x. Let's just write that as 1. And for 7, we came up with a basis that looks like 5 plus 1x. Okay, and there's a nice summary of the